Swayam Prabha. Digital India. Educated India.
So, welcome back friends. So, today we will move to a next set of composites which are called as metal matrix composites. So, till now what we saw was basics of composites, properties of composites. Then we went into different forms of reinforcements which can be done on composites. Then we took matrix as polymer, and then in that we saw under thermoset we saw some processes, and then thermoplastic also we saw some processes. Now from there let us move to metal matrix composites. So here, as the word clearly says, that we use metal as a matrix for reinforcing. Can we use the same processes what we used for polymer composites, or what are the bottlenecks when we use metal matrix as a matrix for composites? So when I say metal generally has very high temperature as compared to that of polymer composites. So content wise we will see introduction, then we will see metal matrix composites, then we will see classification in metal matrix composites, then reinforcement for metal matrix composites, then matrix for metal matrix composites, then advantages, disadvantages with some few applications. From the historic perspective, I am not going into in BC and then coming to AD, just coming in AD in 1939, glass fiber manufacturing came into commercial application. For high temperature electrical applications it came. Then in 1950, boron and carbon fibers were produced for making ropes. Then in 1960, matrix was added to make it polymer matrix composite. 1970s, the Cold War force developed for metal matrix composite for military aircrafts and missile guidance systems came into existence. So metal matrix composite somewhere in 1970s it picked up and it started getting into action. In 1990s, high temperature ceramic matrix composites came, and this started getting into a next generation of aircraft engines and power plants. So from 1970 started the metal matrix composites. So if you see the total shipment of metal matrix composites, so in transportation industry it was around about 31%. So majority came from transportation industry, then came few in construction industry, then in marine, then corrosion resistance equipments which was around about 12%, and electrical and electronics are 10%. Then we have other businesses which were close to 4%. So the market for composites you can see in aircraft industry, missile, basically aerospace industry and marine industry, that means to say transportation industry pushed forward lot on this composites. So you can also see armor materials which were made, automobile and other industrial applications were also made. So this is a figure which is in 1993, which is little old. So when we go to classification of composites, we are now focused into metal matrix composites. So we know composites is made out of a matrix and then a reinforcement. Reinforcement can have several forms. So when we do mix this matrix and the reinforcement, we get something called as metal matrix composite. So what are all the possible matrix? We can have aluminium, we can have magnesium, we can have titanium, cobalt and cobalt nickel, etc. Depending upon your requirements, the matrix can be tweaked into some alloys so that you meet out your requirements. What are all the reinforcing agent? It is alumina, SiC, zirconia, titanium nitride, titanium carbide, cubic boron nitride. So moment I say alumina, SiC, it is very clear that it is very difficult for you to make a long continuous fibers out of it. Once you don't make long continuous fibers, then you can't think of making it mats and other aspects. So today there are technologies wherein which they are trying to make some alumina mats, but generally these aluminas are not continuous. So if it is not continuous, then it has to be only particulate size. So the metal matrix composite can be further classified into particles reinforced metal matrix composite. That means to say, you try to take very small particles with a aspect ratio, that means to say L by D ratio of 1, 2, 3, less than 5. So here we try to take very small particles. These small particles are dispersed inside the matrix. So these composites are called as particulate reinforced metal matrix composite. The next form is short fibers. Short fibers are slightly higher aspect ratio, that is a whisker can be used or a short fiber can be used. So here again the L by D ratio, it changes. So you will have short fibers. It can be made out of, fibers can be made out of glass, or it can be made out of any ceramic materials. So it is dispersed inside a metal matrix so that you try to get a composite. The last one is going to be continuous fiber or sheet reinforced metal matrix composite, wherein which a continuous fiber of glass fiber mat can be used, or any other application, any other small people are today trying to even use cotton for cotton continuous fiber mat, or they are trying to use carbon roving, so as continuous fiber. So they are laying it and then they are trying to get an output. So you can also do sheet laminate, wherein which the metal, in these three cases, the metal will be taken to a liquid state and then brought to solid state. So here what we do is we start with a solid sheet and then we keep the reinforcement, we sandwich it and then we process it to get a composite. So these two applications, continuous fibers finds at high strength applications. We always go for this continuous fiber reinforcement. So when we look into metal matrix composite is a composite material with at least two constituent parts, one being a metal necessary, the other being a material maybe of a different metal or any other material such as ceramic or an organic compound. The definition is the same as for composite. So we have already seen reinforcements can be alumina, zirconia, SiC, TiN, TiC, TiCN, cubic boron nitride, all these things can be used. So matrix can be aluminium, steel, magnesium, titanium, cobalt and cobalt, nickel, aluminium. So when you try to see microscopically what happens when you try to mix it up with the metal. So here if you see, TiN is a ceramic particle. This ceramic particle sits inside a matrix. TiN, these are TiN particles. This sits in a, here it is a stainless steel. So here you see that this sits in a matrix, and this is used for, this is a metal matrix composite, and this is finding applications for wear resistance, that means to say enhanced tribology and strength properties. So what are all the basic demand? See, when you make any product, the first thing which comes to your mind is you have to fix up what is your objective function. So the objective function is always, in terms of composites, is, or I would say it is mechanical properties. Are very important. Then it is also the physical properties. Okay. Then you have the chemical properties, and then at last you have the electrical properties, or electrical properties in fact gets into the physical properties itself. So we are more focused towards physical and mechanical properties. So these are the demands for moving into metal matrix composite. Keep in your mind when we talk about always aerospace application. So aerospace application, it always demands for a lightweight, high strength application. high stiffness application. So, it has low density and it has to have high Young's modulus, the high compression and tensile strength, good process ability, it has to be economical, it has to be mechanically compatible with the thermal stability. Basically, when we try to move out of polymer and get into metals, what we always look forward is slightly high temperature applications. So, in high temperature applications at a higher temperature, the material properties should not change. So, somehow you have to arrest the property expansion or contraction, whatever it is. So, what we do is we add one more phase into it and make sure that it stops that expansion and contraction. So, these are the properties which we always demand from the application point of view. It has to be low density, it has to be mechanically compatible with thermal stability, that means to say high temperature application, then high Young's modulus, high compression and tensile strength, good process ability, that means to say I should be able to produce the required product in a very economical way. So, economical in terms of number of steps involved to reach the output. Second thing is the machine, the capital investment what is involved. Third thing is how reliable the process is to produce the output. You can have a process which produces the output, but if the capital cost is very high, then the processing becomes a challenge. So, you will not have a customer for it. Then finally, it should be economically efficient for applications. The reinforcement, whatever is a material, is embedded into the matrix to enhance or even reduce. If you want to reduce the properties like wear, resistance, hardness, density, porosity, mechanical strength, thermal expansion, contraction and electrical conductivity. See, just as an example, we see all these towers which are there, transmission towers, which transmit power from one place to the other. You see these transmission towers, and these transmission towers are connected with cables, or these cables take the power and it runs for several thousand kilometers to transmit power from the production to the customer. So, this cable this cable is quite heavy, and in order to avoid this cable sagging, they always go for these towers. And the tower's basic function is only to hold the cable. So, as and when you transmit for a longer distance, the cable, when you transmit, it gets heated and it tries to sag. In order to avoid this sagging, so what people do is we add these towers, and these towers are pretty expensive. So, what people have done is they have now started changing this cable, whatever was earlier made out of an alloy, into a metal matrix composites. So, what is the advantage? It has now enhanced properties such that it does not sag very much. So, once it does not sag, the number of towers goes down. So, the initial investment cost of laying for electrification goes down significantly. So, this is another example wherein which the cables are converted from alloys to metal matrix composite. So, it is basically made out of copper metal matrix composites. So, that is what we said, electrical conductivity also. So, we try to enhance the thermal stability, plus we also try to maintain the electrical conductivity. So, here I repeat, the reinforcement is added to reduce the wear or to enhance the wear resistance property, to enhance the hardness, to reduce the density, to reduce the porosity, or if you want, by adding this you can also enhance the porosity. Why is porosity very important? For example, if you want to make think of an application wherein which you wanted to absorb some material. To go further down, you have spilled water on top of a table. You have to remove the water. What we do is we put a porous structure, which is a sponge, just on top of the water, compress it. So, because of vacuum, all the water which is there is sucked, and then we try to squeeze it out. Same way you can also think of applications where in which you want to remove the oxide layer from the top, you wanted to enhance some properties. So, these porosities can be used. Mechanical strength, thermal expansion, and thermal and electrical conductivity is also used. The reinforcement can be discontinuous, can also be continuous. Discontinuous gives me more freedom from the manufacturing point of view as compared to that of continuous. And if you see here SEM, SEM is nothing but a scanning electron microscope. It is on the higher end. So, you can see at a higher magnification wherein which we use electron as a source to look at the microstructure so that we can understand whether the particle is exactly sitting or is there any mismatch between the reinforcement and the basic metal. For example, here we take a metal matrix of Ti6 Al 4V. So, this is the matrix which is a titanium alloy which is taken as a matrix, and we add ceramic particles in to the metal matrix composite. The ceramic particles is nothing but cubic boron nitride. So, maybe this can be used for enhancing the wear resistance. So, we have added this. So, here if you see that exactly at the interface, if there is a poor interface or a weak interface, then these ceramic particles will come out very easily. So, now what people do is, so people always try to see what is the wettability between the alloy and the ceramic particle. If there is a proper interface, then it is good for the from the mechanical point of view. So, in order to see this proper adhering, proper interface, we always go for a scanning electron microscope. So, here it is field emission scanning electron microscope images are done to see the cubic boron nitride getting embedded in Ti6Al V4 alloy. So, here the other one is, you can also see in a stainless steel matrix, you can see CBN sitting. So, here if you see, the CBN are just projecting out, and here the CBN are sitting perfectly inside. So, just by looking at it, at the figures alone, you can compare and say this looks to have a better interface as compared to this. And second thing, when you do this SEM image, you should also keep it in mind, there should not be any agglomeration. Agglomeration means sticking or adhering of the small particles together. So, what happens is, in if you take a cross section of a metal matrix composite, you can have few clusters where in which you can have particles sitting. So, these clusters, what will happen is, they will try to bring in non-uniform properties as far as the metal matrix is concerned. In order to avoid this, it is better to have a visual inspection by using SEM and trying to find out. So, the basic thing is, these particles which are dispersed inside the matrix should not have agglomeration. So, you should make sure that is there. Same way what we studied for polymer matrix composite, the short fibers and other things, there should not be any agglomeration. So, if you look at the different properties potential of different metal matrix composite, so you have property strength, Young's modulus, higher temperature, wear resistance, coefficient of expansion and cost. So, if you look at it, if you take a long fiber reinforced metal matrix composite which is made out of carbon fiber, the properties are very good, Young's modulus is very good, high temperature, wear resistance is okay, expansion is extremely good, but it is extremely costly. So, these types of composites are used for only aerospace application and not in automobile application. So, what is the property of this matrix? The matrix is a monolithic material. Monolithic material into which the reinforcement is embedded, and it is completely continuous. That means to say it is getting dispersed. That is what we are trying to say. In structural application, the matrix is usually a light metal such as aluminium, magnesium and titanium. Structural application where there is load bearing, where it takes load, provides a compliant support for the reinforcement. In high temperature applications, cobalt and cobalt nickel alloys are used, very common. So, this we have already seen. This is the matrix, and This is the matrix and these are the reinforcement. So, most commonly used metal matrix composite is aluminum metal matrix composite, which finds lot of application in automobile, aerospace, construction industry. It also finds in entertainment industry. That means to say very low cost, which is used for some applications. So, aluminium lightweight, so it is used. Next is magnesium, which is much lighter, but it also finds lot of application in aerospace. I have missed one, marine. Aerospace is one. Then copper we have seen in several applications like conductivity, thermal conductivity, electrical conductivity. We always go for copper metal matrix composite, and people today have started using this for wear resistance also. For example, the switch breakers are now made out of copper metal matrix composite, so that it can have a, rather than bimetallic, they are now going for copper metal matrix composite for enhanced life. So, then you have also titanium, which is again used for aerospace. Aluminium, amongst these three fellows, aluminium is the most economical fellow, and then magnesium and titanium are slightly expensive, and processing of magnesium and titanium are little tricky, because we will see that as and when we go. So, metal matrix composite, which I said, aluminium metal matrix composite, which has wide applications. So, aluminium metal matrix composite are usually based on aluminium silicon alloy, and on the alloy there are 2XX and 6, there are several series. So, aluminium silicon, on the other alloys also you can have. So, this series, so every aluminium alloy is given a number. So, with this, by looking at the number, you can quickly go and find out the composition. So, this is used as a metal matrix, and then the reinforcements are generally done with alumina particle or SiC particle. So, this can go for a volume fraction. When I say particle, you should quickly, it should strike how much should be the content. So, the content you can talk in terms of weight percentage or in terms of volume percentage. Generally, we talk in terms of volume percentage. So, volume to weight conversion is nothing but multiplied by rho. Rho is nothing but mass by volume. So, you play with it and you get what you want. So, aluminium and SiC. You can also have continuous fibers of alumina and SiC graphene, long fibers, and you can also have discontinuous fibers of alumina. The metal matrix composite, that means to say aluminium metal matrix composite, are made by three processes. So, one is powder metallurgy route, which is sintering process. We will see sintering process little later. Then we have stir casting, and then we also have infiltration methods. What are the properties? The properties are high strength at elevated temperatures, high modulus, low density, high thermal conductivity, excellent abrasive resistance. See, when you have a metal matrix composite, you have ceramic particle setting. So, these are ceramic particles which are reinforced. So, what happens when you have any tribological application, when there is a ball or a flat surface moving, so these fellows will try to prevent the contact between the sliding surface ball and the base material. And then what happens when it tries to protect this fellow, he always tries to reduce the wear. So, this is what is abrasion wear, right. So, it is used for automotive parts like piston, push rods, braking components, then brake rotors for high speed trains. Bicycles today are made out of metal matrix composite. Today you have very light bicycles coming out. First stage, all these bicycles moved from steel frame to aluminium frame, where the weight reduction was there. From aluminium, today they have gone to carbon composites, which are much more lighter, and all the parts which are made out of aluminium metal matrix composite. So, golf clubs and then electronic substrates, then cores of high voltage and electric cables are made out of it. when you go to magnesium metal matrix composite, are generally reinforced with SiC particles. So it is low density, high stiffness, high wear resistance. It has good strength at elevated temperatures. It has also good creep resistance. We already studied what is creep when we studied the mechanical properties. I would request you to go back, look into the slides and get that information. So it is used in racing cars, automobile braking system, aircrafts, gearbox, transmission and compressors and engines. Then copper metal matrix composite. So continuous fiber of carbon, SiC can be used, tungsten can be used, stainless steel it can be used. So the process for making copper metal matrix this powder metallurgy and infiltration. Same way when you talk about magnesium, it is also the same. So we have the same processes: powder, metallurgy, stir casting and infiltration for magnesium also. So again the properties: low coefficient of expansion, then high stiffness, good electrical conductivity, high thermal conductivity, good wear resistance. Here we don't talk about density because copper density is high. When you go to titanium, so titanium metal matrix composite are continuous monofilament silicon carbide fiber. So when you talk about silicon carbide fiber, is basically you have a metal fiber and on top of it they keep coating by CVD process the silicon carbide. So what is a problem with this thing? When you have a curved surface, the mendability becomes a problem, or the corner radiusing becomes a problem. So when you talk about titanium boride, TiB2 and TiC, these are some of the particles which can also be reinforced with titanium metal matrix composite. Predominantly what we use is powder metallurgy route. So here the strength comes, stiffness, creep resistance, thermal stability, wear resistance is also there. Okay, and it is also lightweight. So here F-16 jet landing gears are made out of it. Turbine engine components, high temperature, fan blade, actuator piston, synchronization rings, connecting links, shafts, discs are made. Automotive engine components are made. Drivetrain parts are made and other general machine parts are made out of titanium metal matrix composite. If you look at titanium metal matrix composites which are used for structural application in F-16 jet landing gears, so you can see here this is a sandwich structure, which is a foam, a metal foam, and then it has reinforcement on the top. So reinforcement at the top and the bottom, these are reinforcements and the reinforcements plus matrix is also there. So it is a skin, the skin is there, you have a core and then you have one more skin. Depending upon your requirements, you can try to use it. This core, whatever I said, this can be a foam, and the foam can be of two types. It can be a metal foam or it can be polymer foam. So here in this application they are made out of metal foam. So what are the applications? So high temperature capability, fire resistance, okay, high transverse stiffness and strength is there, no moisture absorption. In polymers you have the problem of this hygroscopicity, but here it is no moisture absorption. It is highly conductive in terms of electrical and thermal, better radiation resistance, high strength and modulus you have, low thermal coefficient of expansion, and when you use this whisker and this thing are used for conventional metal equipments, can be used for fabricating these type of composites. But the main disadvantage, it is not economically getting competed except for the transportation industry where aluminium metal matrix composite is used. So that is competing with aluminium alloys, and people have changed a lot, and keeping efficiency, energy efficiency, titanium alloys have got into the aerospace industry, but still it is very expensive for for a regular customer to use, and relatively the technology is immature. That means to say the consistency in the product output when you use for a large areas are even now a challenge. There are few companies who have learned the skill and they excel out, but others, they always try to make the rejection rate somewhere while making metal matrix composite varies from 10 to 20%, depending upon the size and shape and accuracy, whatever it is. The complex fabrication method for fiber reinforcement is always a challenge. So if it is a particulate reinforcement, it is very easy. Fiber is always a challenge. So people still have lot of challenges with respect to fabrication using long fibers and using even weaved fiber mats for metal matrix composite. Today people are working on take glass fiber mat and then try to infuse metal matrix. The only problem is these glass fibers are very light. So if you want to make several layers, laminates, and then if you want to infuse, these reinforcements displace from their existing position, and we are not able to controlly flow the metal matrix into the glass fiber. So today we end the lecture with a small assignment, and again it is for your own self learning. What kind of composites do you suggest for biomedical application? Whatever we have seen, what are we seen? We have seen aluminium, titanium, magnesium, copper. Which one? Cobalt. Which one do you suggest? And if you suggest anything, say for example you suggest aluminium, then suggest why did you choose this composite. So I repeat, you are supposed to choose a composite for biomedical application. So after making your choice, please try to list down all your essential properties and justify your answer that this is the best as compared. So basically what are you supposed to do? You are supposed to look into when it gets into the body, its density, its strength. When you talk about strength, you look at yield strength, you look at E, you look at toughness, then you look at corrosion resistance. Because in our body we have blood which has a pH. So you have to find out what is the pH and which material is conducive for it, and then choose the proper composite material. So with this we come to an end of this lecture, and this assignment is self-learning for you. Please take it seriously. Do lot of search in internet. You get lot of material. From there you can try to choose it. Thank you very much.